All right, welcome back to Real Analysis. Still working in Chapter 7, results about differentiable functions. In fact, we're still working in Section 7.3, kind of moving along one subsection at a time. This time we're going to be looking at the third subsection, and it's about the derivative of a differentiable function that has an inverse. Okay, so you've seen stuff like this in calculus, probably used to derive formulas of things like the derivative of the logarithm, which is the inverse of the exponential, the derivative of the arcsine and arctangent. Those are the inverses of the trigonometric functions sine and tangent, respectively. So it's actually kind of a general recipe that you can use anytime you have an invertible function. It's differentiable somewhere. You can show that its inverse is also differentiable and work out a formula for the derivative of that inverse. So that's our goal. Our goal, I've got it written here, is to show that if you take some function on an interval, I will continue to be an interval, and it's differentiable on that interval, and it also has an inverse. So there's some function you can compose with it to get the identity. Then the inverse function is also differentiable, well, provided that the derivative is not zero. We'll give an example to show that if the derivative of this invertible function is zero at some point, then its inverse will actually fail to be differentiable at the image of that point. All right. So we're going to borrow a little bit of machinery rather than circling back. Most of this stuff we actually have the tools available. I'm just not going to circle back. We never really carefully characterized what an interval is. So sometimes actually proving something is an interval for us, we need some kind of characterization. It's not out of the scope of our course, but we just didn't do it. So for purposes of this lecture, I'm going to borrow the kind of following facts: that if you take some interval and a continuous function on that interval, say called f, then its image is also an interval. It's not much of a stretch to say that that's what the intermediate value property says. Yeah, but there's a little bit more to it than that. In fact, if the interval is a closed bounded interval, the extreme value theorem and the intermediate value theorem actually give that. That's an exercise you could stop and kind of think about right now, that if you take a continuous function on a closed bounded interval, well, then those two theorems, extreme value and intermediate value theorem, together show that the image is also a closed and bounded interval. So you can work that out. But I'm just going to kind of borrow it right now, that if you take the continuous image of an interval, you get an interval. Okay. And then one more thing I'm going to assume here without proof in this particular lecture, you can ask me about it in an office hour if you want to, is that if you take some continuous, so I'm still assuming f is continuous, and it's strictly monotone, that is, it's strictly increasing or it's strictly decreasing, then it will have an inverse. So you guys kind of proved something like that in a homework problem before when we were talking about countability. Yeah, a strictly increasing function has to be one-to-one, and it is therefore onto its range. So it's an invertible function. And the inverse, which I'm going to denote by g here, g is just f inverse, so it would have the domain equal to the image of the interval I under f, that function is also strictly monotone and continuous. Okay, so that's something that, again, I'm going to kind of omit the proof of from this conversation, but in a nutshell, if my stammering made that hard to understand, I'm just saying that if you take a monotone continuous function, it'll have an inverse, and its inverse is also a continuous function. Okay, so we're going to just kind of use those. I'll refer to them below as our borrowed facts. You can ask me about them in an office hour, or better yet, prove them yourself. They're within your reach. Okay, so here's the first theorem. Don't be intimidated by a long, complicated theorem statement. When a theorem statement is this long and complicated, it kind of means the proof has to be easy. The hardest part is just wading through what the theorem says. So, okay, so let's take such a function. I've got an interval I, I've got a function defined on I. I'm assuming it's either strictly increasing or strictly decreasing. I don't care which one. I'm assuming it's continuous. All right. So there's just sort of my assumptions about this f, continuous monotone function on an interval. I'm going to call the image of that interval j, and our borrowed fact says j is also an interval. Okay. So then I'm going to let g denote the inverse, and our borrowed fact says that it's monotone and continuous. All right. So g is the inverse of f, meaning that they undo each other. That g of f of y is y, f of g of x is x for all x and y in their respective domains. So that's all the assumption, okay? So what does the theorem say? It says that if f is differentiable at some point in this interval and its derivative's not zero there, then g will be differentiable at f of that point. So I'm just going to call it y naught for short. And then here's the formula. The derivative of g at y naught is 1 over the derivative of f at x naught. And x naught, because g and f are inverses of each other, you can look right here when I say this. If y naught is f of x naught, then x naught is g of y naught. So you can replace that, right? F and g undo each other here. I can write it in over here. That g is the inverse of f. So if y naught is f of x naught, then g of y naught is x naught. Okay, so that's what I want to give a proof of. That's what I want to give a proof of, and I'm going to use the Carr-Theodori condition to do it. So using the a statement of the theorem to set the notation. So I know what f is, I know what g is, I know what I'm assuming about them. Let's pick some point, x naught in the interval. F is differentiable at x naught, so let's bust out Carr-Theodori. Carr-Theodori says that there has to be some continuous function phi on the same interval that f is defined, and I'll use the same color as the Carr-Theodori lecture. Here's Carr-Theodori's equation, that for every x in the interval I, f and phi satisfy that equation. Yeah, phi is kind of the difference quotient, if you like, for the function f on this interval. And moreover, we know a little bit more. Phi's value at x naught is f prime of x naught, which in this theorem we're assuming is not zero. Okay, so that's using the differentiability of f. We get that Carr-Theodori condition. Okay, so phi is a continuous function. It's not zero at x naught, so there's a neighborhood upon which phi isn't zero. That's a theorem from chapter 5. If a continuous function isn't zero somewhere, there's actually a neighborhood of that point on which it's not zero. So there's a little open interval centered at x naught that g is not zero on. I'm calling that open interval n sub epsilon of x naught. Of course, that whole interval might not be in I. That's why I'm intersecting it with I, right? Because I need to make sure that it makes sense to plug in into the function phi. So what am I going to do? I'm going to define u to be the image of that intersection. So I'm taking this little neighborhood around x naught where phi is not zero. I'm intersecting it with I, so I'm staying in the domain of f, and I'm taking f of it, okay? So u is going to be some subset of the image of the interval I, some subset of j, okay? F and g are inverses of each other. F and g are inverses of each other. So for every y in u, if you take g of y and then take f of that, you're going to get y back, okay? So every y in the interval, or in the set, excuse me, u would satisfy that because f and g are inverses of each other. So I think we've already said this above. Let me let y naught equal f of x naught. So then if I take any y in u, I'm kind of thinking Carr-Theodori here, so I'm going to switch my highlighter color. If I look at y minus y naught, well, y, we just wrote above, is f of g of y, so I'm going to replace that. Y naught is f of x naught. And by the Carr-Theodori equation up above, because remember, where are these things? These g of y's and I'm using the Carr-Theodori equation. Let me come back up here and see if I can zoom out. Sorry about my pause there. So what I'm using is this thing, right? So I need to make sure that the things that I'm plugging into f and these things over here, they have to come from the interval I. Okay, well, so g of y is certainly in the interval I because y comes from u, and when you take g of something in u, you're going to get something back in I. Okay, x naught comes from I because we've assumed that the whole time. G of y is in I, and the g of y is in I, and g of y naught is x naught. That's where my brain kind of hiccuped on me here, that g of y naught is x naught because g and f are inverses of each other. So what I'm talking about here that I kind of stammered on is this Carr-Theodori equation. I'm applying it to the x value is g of y and x naught is g of y naught. So that's all I'm writing down here. So I've got the left-hand side is f of g of y minus f of y naught, or g of y naught, is phi of g of y times the quantity g of y minus g of y naught. So that's just from the Carathéodory equation. Okay, good. Sorry about the stammer there. Okay, but now let's return. So y came from u. So g of y is certainly back in the set that u was the image of. Remember, g is the inverse of f. So u, if I scroll back to show you where it was defined, u is just f of that intersection. So if I take g of something in u, I'm going to get something back in this set, right? So that's all I'm writing down here. So in particular, phi of g of y isn't 0 for every y in u, because remember, phi wasn't 0 on that set. So why am I worrying about that? Well, I'm worrying about that because I want to divide this equation by phi of g of y, and I need to make sure it's not 0, and I just did. So I'm just rearranging this thing now. If I kind of show you what terms I'm looking at, I'm taking the g of y minus g of y naught. It's over here now. I divided both sides by phi of g of y, so I end up getting the difference in the f's, or excuse me, I end up getting y minus y naught divided by phi of g of y, okay? And that equation, I've labeled it hashtag over here, or pound. That's true for every y in g. And it looks kind of Carathéodory-like. Looks Carathéodory-like to me. So what do I need to verify? I need to verify that this thing is a continuous function. Okay, and it is a continuous function because why? It's the composition of phi and g. Well, it's 1 over it. Well, phi and g are both continuous, so their composition is continuous at y naught. And moreover, the value there is not 0, so the reciprocal is continuous at y naught. The respective theorems are 543 and 540. Okay, so that thing, equation hashtag equation pound, by the Carathéodory equation, it says that g is differentiable at y naught, right? Because I've got the difference of the g's is this continuous function times the difference of the inputs. And moreover, if I take the expression here, the 1 over phi of g of y, its value at y naught is the derivative of g. So that's what I'm going to write down here to end this proof, is that the derivative of g at y naught is that continuous function's value there. But we've already said g of y naught is x naught, so that's just phi of x naught. But phi of x naught from the original application of Carathéodory was f prime of x naught. Okay, so that completes the proof. There's the formula that the derivative of this inverse function is 1 over f prime at the original input. Whew, nice. All right, stop the video and kind of soak that in. I'm just going to keep going. I wanted to make a remark that you cannot do away with the hypothesis that f prime is not equal to 0. Because if you look at the conclusion of the theorem, if f prime, another way to think about the conclusion of the theorem, when we write that g prime is 1 over f prime, well, that means their product is 1. So if f prime of x were 0, that seems to be a problem. I don't understand how 0 times this derivative of g could be 1. So that hypothesis is absolutely crucial. And in fact, if you want a specific example, if you take the cubing function f, it's strictly increasing, right? F x equals x cubed is a continuous differentiable increasing function. I wrote here at x0 equals, I didn't put the equals. I meant look at this thing at x0 equals 0. Okay, so the inverse function of the cubing function is of course the cube root function, but the cube root function isn't differentiable at 0. Probably saw that in calculus. Why? It's because f prime of 0 is 0. Nice. Okay. This one, don't worry, it looks like another terribly long theorem, but I'm just going to kind of say that what we were doing above was for kind of points. You can, if it's true for the whole interval, then you also get a theorem. So what are we assuming here? We've got an interval I, we've got a function defined on it. It's strictly monotone, so increasing or decreasing on I. We're going to let J be the image of the interval I under F. And then by a borrowed fact, we know that the inverse function exists. Okay, so a strictly increasing or strictly decreasing function has an inverse, but I'm not assuming this time that G is continuous. So it's a little bit stronger of a theorem. So the condition is that if F is differentiable on I and its derivative is never zero, okay, so not just at a single point, but on the whole interval, then G is differentiable, and the same formula holds. That G prime is 1 over the composition of F prime with G. So we don't have to recapitulate the entire proof above. We just need to show that the hypotheses of theorem A are satisfied here for every X and I. That's going to be our proof. So I'm just going to kind of do this in checklist style. You might want to, if you didn't write down the hypothesis of theorem A, you might want to scroll back and do it right now. But one of the things we need to do is check that F is strictly monotone on I. Well, that's given here. That's also part of the hypothesis in this theorem. Okay, we have to check that F is continuous on I. Well, it's continuous because it's differentiable. Differentiable functions are always continuous. Okay, we have to check that J is the image of F of I. We're assuming that, and that G is the inverse of F. Those are hypotheses in this theorem. We have to check that G is strictly monotone and continuous. Well, that's borrowed fact number 2. Borrowed fact number 2 says that if you have a strictly monotone increasing function or monotone continuous function F, that its inverse, which I'm calling G, is also strictly monotone and continuous. So that's from our borrowed fact. And then we have to show for every X that F is differentiable at X and its derivative isn't 0. That's one of the hypotheses of theorem A. We're assuming that here. Okay, so all the hypotheses of theorem A hold, so the conclusion holds. So for every Y, if you take the derivative of G at Y, the theorem says, well, that's 1 over F prime of X, and what's X? It's just G of Y. So that's kind of the more general statement. The work was done in theorem A. This is just sort of saying that if it's true for every point, then you get a theorem about the whole function. Okay, so I want to keep this video kind of short. I'm just going to illustrate this stuff for a couple of times. That second theorem, I'm calling it the derivative of the inverse theorem. So that's what this DIT means, derivative of inverse theorem. And I want to use it to calculate the derivative of the inverse sine function. Okay, so I'm going to be assuming some things about the derivative of sine here that we haven't proved in this course, but you're familiar with calculus. So let me take the function sine of x, but of course it's not invertible over its entire domain. So I'm going to restrict it to the open interval from minus pi over 2 to pi over 2. That's the traditional interval to restrict. So on that interval, sine is strictly increasing and continuous and differentiable. And in fact, its derivative is the cosine function, which again, on this interval is never 0. Stop the video and verify that that makes sense. Okay, so the derivative of sine is never 0 on the interval from minus pi over 2 to pi over 2. The sine function is strictly continuous, strictly increasing and continuous there. So the derivative of inverse theorem applies, okay? So if I take the image of the interval from minus pi over 2 to pi over 2, I get the open interval from minus 1 to 1 sine function. So the inverse function, the arc sine, if you like, is defined from minus 1 to 1 and takes on values from minus pi over 2 to pi over 2. And this is the notation I'm going to use for it. Arc sine. You can also use sine to the -1, but I prefer this arc sine notation. And the derivative of inverses theorem says that it's a differentiable function. G is differentiable. And its derivative is, well, 1 over the derivative of the sine evaluated at the arc sine of y. But here I'm going to use a little trig function identity here, that the cosine of some number, you can always rewrite it as the square root of 1 minus the square of the sine of that number. That's from a familiar trigonometric identity. If the cosine is positive, which it is in our case here, I don't need to put a plus or minus because of the range that we're looking at. So if I just replace that denominator with that square root, one reason that's kind of nice is because the square of the sine of the arc sine of y is just y. So there's the formula for the inverse that I'm after. Okay. So by the derivative of inverse formula, the derivative of arc sine is at y is this familiar formula, 1 over 1 minus the square root of 1 minus y squared. Cool. All right, I'm going to kind of look at one more application of this, the kind of so-called general power rule. In your homework, I'm not going to do it here, but in your homework, you're going to show that if f is the polynomial function x to the n, it's differentiable and its derivative is given by that familiar formula. So that's a homework problem of yours. So I'm going to use the derivative of the inverse function in the case that n is equal to 2 to derive a formula for the derivative of the square root function. So just to kind of run through the terminology one more time. So this time I'll define f on the strictly greater than 0, because remember I can't have derivatives that are 0. F is the square root function. Okay, so its domain is 0 to infinity, open, it's strictly increasing, its image is 0 to infinity, so the inverse function's domain is 0 to infinity, and the inverse of it is y squared. I'm going to let you check the details, but on that open interval from 0 to infinity, y squared is strictly increasing, differentiable, and its derivative is 2y. That's from your homework problem. Derivative of y squared is 2y, or we actually proved that in class as well. So the derivative of the inverse theorem applies, and it says that the derivative of f, the inverse of g, the character names have switched roles here, by the way. So g is the differentiable function, f is its inverse. The derivative of inverse theorem says that f's derivative is 1 over g prime of f of x. Well, g prime is 2 times its input, so that's 2 times f of x, but f of x is the square root of x. Okay, so there's that familiar formula for the derivative of the square root. Or if you write that as rational exponents, it kind of looks like it extends the power rule. The power rule works for this, at least this fraction, x to the 1/2. The derivative of x to the 1/2 is 1/2 x to the minus 1/2. In your homework, I'm going to ask you to look at the derivative of any rational exponent, m over n. I actually restricted it to just natural numbers, but you can do the more general problem if you want. And this example in this video is supposed to be helpful to do that. Okay, so that's it for the video. Thanks for listening.